Hello, my name is Isabella Rangos, and this is Lab 4, Circuits and Capacitors. In this lab, I explored the time-dependent voltage and current flow in DC and RC circuits. I created computational models that simulate series circuits containing bulbs, batteries, capacitors, resistors, ammeters, and voltmeters. I then measured the potential difference across a closed circuit, modeled parallel circuits with charging and discharging capacitors, and finally, modeled the time-dependent voltage of an RC circuit. The fundamental physical principles for this lab experiment include conservation of charge, conservation of energy, otherwise known as the Kirchhoff loop rule, which says that the potential difference around a closed loop is equal to zero, and finally, Ohm's law, which allows us to calculate the current. Here's my computational model of a series circuit. I predicted that currents I1 and I2 would be equal to 0.02 amps, as measured by the two ammeters. This prediction was correct, as the modeled ammeters generated the same result. When one of the ammeters was inserted backwards and the connections to the ammeter was reversed, the ammeter read negative 0.02 amps. When a voltmeter replaced the ammeter, I got completely new readings. The ammeter read 0 amps and the voltmeter read 3 volts. The voltmeter reads 3 volts due to the connection to the two 1.5 volt batteries. However, the circuit is now open and therefore no current runs through, and thus the ammeter reads 0 amps. I then reclosed the circuit with a wire and used the voltmeter to measure the potential difference at each different connection series across the circuit. I recorded my data in the chart above for the potential difference between each two sets of points. The total sum for the potential differences is 0 in accordance with the loop rule that says that the total potential difference in a closed circuit will equal 0. Here is a graphical representation of the potential difference between each series of points. When the voltmeter is attached, the ammeter reading does not change because the circuit does not flow through the voltmeter, as it is not part of the closed circuit. When the voltmeter is attached across the 100 ohm resistor, the ammeter therefore stays at the same reading of 0.02 amps. When the voltmeter is replaced with an ammeter in parallel with the 100 ohm resistor, the current through the other ammeter increases to 0.06 amps. This is because the 100 ohm resistor is essentially bypassed, as all of the current flows through the ammeter instead. I used the results and observations from the first part of the experiment, as well from the parallel circuit experiment, in accordance with Ohm's law to calculate the resistance of each of the circuit elements listed above. The calculations are included. I then created my computational model for an RC circuit using both a 10 ohm bulb and a 20 ohm bulb. When I created the circuit with a battery, the bulb initially lit up and slowly grew more and more dim as the capacitor was charged. When the capacitor is connected directly to the bulb and the battery is removed, the same reaction occurs, but this time the capacitor is discharging. In both cases, current is flowing through the circuit. I measured the times for the charging and discharging and recorded them in the graph above. Finally, I set up a circuit using a 30 ohm light bulb and measured the voltage across the capacitor using a voltmeter as it discharged, beginning with a full 9 volt charge, equivalent to that of the battery in the initial setup. I then graphed the natural log of the potential difference divided by the initial voltage over time. The results are displayed above. The RC time constant allows us to measure how long it takes a capacitor to charge to a specific voltage level. The measured RC from this experiment is equal to -1 over the slope of the graph from the previous results, which in this case calculates to 5.9988 seconds. This is extremely close to the computational model's value of 6. What if we used a real ammeter instead of the simulated ammeter? The current output read by the ammeter would be lower in real life because the real ammeter provides a minute amount of resistance that is not simulated in the computational model. What if we used a real battery to charge the capacitor versus the simulated battery? This would have a similar result in that the capacitor would charge slower in real life because the real battery and capacitor provide minute amounts of resistance that are not accounted for in the computational model.